we started with the concept of isolability in order to understand more complex carbonyls. And thus far, we have applied the concept of isolability to organic fragments. And you've seen that you can easily apply the octet rule in order to derive the number of electrons and the number of frontier orbitals. Okay, and when the number of electrons, frontier orbitals of molecular fragments are the same, then they're being called isolable. Now you can extend this concept also to organometallic fragments. It's just that you do not apply the octet rule, but you apply the 18 electron rule. Okay, so that means that the number of electrons and the number of frontier orbitals is given by 18 minus the number of valence electrons the organometallic fragment has. Okay, so for instance, we have seen that the element manganese makes a dimeric carbonyl of the composition Mn2 CO10. Okay, and that is because, as we said, we have 217 valence electron fragments that are being combined to make this dimeric carbonyls. We could, however, also now use the concept of isolability in order to derive the same. Okay, you could say that an MnCO5 fragment has one electron and one frontier orbital, because 18 minus 17 is 1. Okay, and then the two MnCO5 fragments are isolable to each other so that you can combine them to form a stable molecule, which then would be the dimeric carbonyl. So now one can, of course, not only combine two organometallic fragments to make a stable molecule when these organometallic fragments are isolable, one can also combine isolable organic and organometallic fragments. So, for instance, we previously determined that the methyl group also has one frontier orbital with one electron in it. Because of that, the methyl group should be isolable to the MnCO5 fragment. Therefore, it should be possible to combine a methyl fragment with an MnCO5 fragment to produce a stable molecule, which would be this molecule here. And indeed, this molecule is known to be stable, and with the help of the concept of isolability, we can now explain or understand why. So now one can extend these ideas to many other fragments. So for instance, we can consider an FeCO4 fragment. Okay, so what is the number of valence electrons in this fragment? We can use our electron counting method in order to determine this. So we have the iron, which has 8 electrons, okay, and then we have 4 carbonyls, which have 2 electrons each. So 4 times 2 gives 8, and 8 plus 8 gives 16. So this means that we have a 16 valence electron fragment here. Okay, so now we have to determine the number of frontier orbitals, the number of electrons in these frontier orbitals, just by subtracting 16 from 18, and that gives 2. Okay, and for that reason, it should be possible, at least according to the concept of isolability, to combine 2 FeCO4 units, okay, which are each 16 valence electron fragments which are isolable to each other, to make a dimeric molecule with an iron-iron double bond. However, this is not realized by nature, because there's another possibility to make a molecule that satisfies the concept of isolability. So instead of making a double bond between two iron atoms, we can also make a triangular cluster in which each iron makes a single bond, or makes two single bonds to neighboring irons. And so we have a trimeric cluster of iron tetracarbonyl fragments. Okay, so instead of a double bond, there's also the possibility to make two single bonds, and in this case, nature utilizes that possibility because in this case the resulting molecule is more stable. Okay, so now if we wanted to combine the FeCO fragment with an organic fragment, what organic fragment would be isolobal? Okay, so how many valence electrons should this isolobal fragment have? It should be a 6th valence electron fragment, because 8 minus 6, that gives also 2. Okay, and that would be, for instance, a CH2 group. Okay, and indeed one can make so-called carbine complex, and the carbine complex is defined as a complex between a metal and a ligand via a metal carbon double bond. Okay, so in this case we have a CH2 group bound to iron via an iron carbon double bond. Okay, and this is something that nature realizes. So it doesn't realize an iron-iron double bond, but it can actually make an iron carbon double bond. Okay, so now we can go from an FeCO4 fragment to a cobalt CO3 fragment. So how many valence electrons would we have in this case? Well, the cobalt has how many electrons? It has 9, right? It's in the 9th group in the periodic table. And then we have 3 carbonyl units contributing 2 electrons each. That's 6, and 9 plus 6, that gives 15, correct. So we have a 15 valence electron fragment, and therefore, how many frontier orbitals with how many electrons in it would we expect? Well, that's just 18 minus 15, and that's 3. So we could imagine that 2 isolobal cobalt CO3 fragments make a dimeric molecule with a cobalt-cobalt triple bond. But again, nature doesn't realize this possibility. The carbonyls have a tendency to make clusters instead of multiple bonds, and therefore, like in this case here, a cluster molecule is being preferred, and in this case, the cluster molecule would have to have 3 single bonds, okay, and each cobalt would need to make 3 single bonds to 3 neighbored cobalts. And that can be realized by the formation of a tetrameric tetrahedral cluster. So when you look at a single cobalt here, you can see that each cobalt makes 3 single bonds to neighbored cobalts. And that's true for all the cobalts. Okay? So you see that with the help of the concept of isolability, you can fairly easily understand such a cluster and the stability of such a cluster. Otherwise, by just looking at this cluster, one would say, nice complex molecule, but why does not nature make something like that? The concept of isolability gives you a nice, simple answer to that. So now one could, of course, also thinking about combining the organometallic fragment with an organic fragment. In that organic fragment would then need to be a 5 valence electron fragment, because 8 minus 5 gives 3, meaning 3 frontier orbitals with 3 electrons in it, and that would constitute isolobality to the cobalt CO3 fragment. So one could therefore imagine a molecule in which a CH fragment, a 5-valence electron CH fragment, would combine with a cobalt CO3 fragment to make what is called a carbine complex. So a carbine complex in general is a complex in which there is a metal carbon triple bond. And indeed, nature realizes such carbine complexes, and the help of the concept of isobality, we can easily understand the stability of such complexes. All right. So there's a sum we can say double and triple bonds between carbonyl complexes are not known. Instead, clusters with metal-metal single bonds are being realized. Okay. So now just how can you actually make such a cluster carbonyl? So for instance, you can make this cobalt tetrameric cobalt cluster simply by thermal decomposition of the dimeric cobalt cluster you encountered in the previous class. So above 40 degrees Celsius, this dimeric cluster tends to become thermally unstable and lose CO. We could drive away the CO from the reaction mixture, and that forms then the tetrameric cobalt cluster. Okay, one can also make the higher homologues, the rhodium and the iridium, and these even form spontaneously from the elements. Remember, when we discussed the carbonyls of group 9, we said we can make the dimeric cobalt carbonyl, but not the higher homologues, and that's because the higher homologues actually tend to make the tetrameric clusters here, with 15 valence electrons in each fragment directly. All right. So here are just some structural details. So when you look at the exact structure of the cobalt and the rhodium tetrameric clusters, you see that there's actually one cobalt which has only terminal COs, while the other 3 cobalts have 2 terminal COs and one bridging CO. And for the rhodium, it's the same, but for the iridium, you have only terminal COs, and that's actually a general rule. Only 3 and 4D elements can have bridging COs. 5D elements like iridium can only make terminal COs, and it's easily understandable because iridium is the heavier element. So for that reason, the iridium distances are longer. So therefore, it's more difficult for the CO ligand to bridge to iridium atoms. Okay, then let's build further on that. Can we also make isoelectronic charge carbonyl clusters by changing the elements and adjusting the charge, similar to what we have done previously with the simple carbonyls? And in principle, it is possible, but not all the molecules that you can construct on a sheet of paper are necessarily found in nature and are stable. And there are certain reasons for that. So let's go through that by a number of examples. So we've seen that the cobalt CO3 fragment is a 15 valence electron fragment and makes this tetrahedral tetramer. So now, for instance, we can replace the cobalt by iron So the iron has 1 electron less than the cobalt. So with respect to the 15 valence electron fragment, FeCO3, therefore would need to have a 1 negative charge. So now that, or 4 of these could again, well, tetramerize to make a tetrahedral cluster. But this is an example of where nature doesn't realize that possibility that exists on a sheet of paper, and one can of course try to rationalize why. And one reasonable explanation is that a 4- charge on this carbonyl cluster is already too high. We have learned that high negative charges tend to destabilize the metal bonds in carbonyls, and we can apply this argument here in order to understand why this cluster is not stable. So now we would have another possibility to realize 15 valence electrons. We could assign the iron a positive charge and add 1 carbonyl ligand. So the added carbonyl ligand would add 2 electrons. Therefore, in order to maintain our 15 valence electrons, we would need to adjust the charge from -1 to +1. However, a tetramer of this fragment is also not known. So again, we would have a positive charge. In this case, it would even be a high positive charge, which is even less favorable than a high negative charge. But in addition to that, also the coordination number would be too high. So if we add 3 iron-iron bonds to the 4 iron-carbon bonds, that gives over 7 bonds. We would have a coordination number of 7. And that's just highly unfavorable for carbonyls in general. Okay, for similar reason, also other fragments are not stable. So for instance, we could go from the iron to the manganese. So the manganese has 1 electron less than the iron. So an MnCO4 fragment would also have 15 valence electrons. So that would be a neutral species, but again, it's not observed because the coordination number would be too high, it would be 7. So then we could even go from the manganese to the chromium. Then the chromium would have to carry a negative charge because the chromium has 1 electron less than the manganese, but again, the coordination number would be too high. And if we added a carbonyl ligand and adjusted the charge of the chromium from -1 to +1, we would even have a coordination number of 8, and that would be, of course, also unrealistic. So this means that the concept of isolability has limitations. Okay, you cannot safely predict that when two fragments are, or 2 or several fragments are isolable, they have to make a stable molecule. Okay, there can still be reasons that prevent that. So we always have to carefully think about, are there perhaps other reasons why my molecule could still be unstable? For instance, when the coordination number is too high, when the charge is too high, and so forth. Okay, so one can do more with this. So we can also apply the same ideas to our tri-iron dodecacarbonyl here and replacing the iron systematically. So for instance, we can replace the iron by manganese. The manganese is 1 electron less than the iron. So the respective fragment then needs to have a 1 negative charge. So we would need to trimerize 3 of these. And in this case, we can successfully do this. So the respective trimer is known. So the coordination number wouldn't be unfavorable in this case. Also, the charge for a minus is still acceptable. So now again, we could add carbonyl ligand that would add 2 electrons. That means that we would have to adjust the charge at the manganese accordingly, going from -1 to +1. But this again does not make a stable complex because the coordination number would be high. If we add 2 bonds to the 5 manganese carbon bonds that already exist, that would get 7, and the coordination number of 7 is not good for carbonates. Okay, for the same reason, also a chromium pentacarbonyl trimmer would not be stable, coordination number would be too high. Could also go into the other direction, replace iron by cobalt, so the cobalt would have 1 more electron than the iron, so the respective fragment would therefore have to carry a 1+ charge, but that's also not known because it's a positive charge, and 3 positive charges are already too many. We could remove 1 CO and adjust the charge from +1 to -1. So this is actually also not known. It's in this case a little more difficult to understand why, because it would only have a 3 negative charge, okay, and a coordination number of 5, which is not too bad usually, but nonetheless, this molecule has not been successfully synthesized this far. That's wrong. All right. So generally, we can say as a rule for carbonyl clusters, no positive charges and no high negative charges. Should avoid high coordination numbers larger than 6. So 6 is always ideal. Anything less than 6 is less favorable. Okay, so now one can do more with the concept of isolability in carbonyl clusters. We can now systematically replace some of the organometallic fragments in the clusters by organic fragments. We can understand why this is possible, again, using the concept of isolability. So let's have a look at our tri-iron dodecacarbonyl here. So one possibility is to replace one 16-valence electron FeCO4 fragment by an organic 6-valence electron fragment, okay, which would be isolable to the 16-valence electron fragment. So that could be, again, for instance, just a CH2 group. So it should be possible to replace an FeC4 unit by a CH2 group, and the respective molecule is indeed stable. We can call this a mu methylene complex because here a methylene CH2 unit bridges to iron atoms. Okay, now we can do this not only one time, this substitution, but multiple times. So we can now also replace a second FeCO4 unit by another CH2 unit. And that gives you then this molecule here. And this molecule can be conceived as an ethene complex in which an ethene molecule binds side-on to this FeCO4 unit. Okay? And the bond order in the ethene is reduced from 2 to 1 because the respective electrons are being used to make the 2 carbon-iron single bonds. Okay? So we're again sacrificing the bond order between the 2 carbon atoms in order to make carbon-iron bonds. So last but not least, we can even think of replacing all organometallic fragments by organic fragments, and then you would arrive at the cyclopropane molecule. So now we can do this with the tetrameric clusters as well, just according to the same logic. It's just that we have to replace a 15-valence electron organometallic unit by a 5-valence electron organic unit. So we have previously seen that a 5-electron unit is a CH fragment. So we can replace CO3 unit by CH unit. Okay. So you see, with the help of the constant isotope value, you would understand the stability of this complex. So we can call this a mu3 methine complex because a methine CH unit bridges 3 cobalt atoms. So now again, we cannot do this only once, we can also do this multiple times, that substitution. So we can substitute another CO3 fragment by another CH unit. And then we arrive at this tetrahedral molecule here. This one can be conceived as a mu2 hepta2 ethine complex. So one can understand this complex as a complex in which ethine with a carbon-carbon triple bond binds side on to this dimeric carbonyl cluster. And well, the 4 electrons that are in the 2 carbon-carbon pi bonds are being used in order to make 4 single bonds. Okay? So this carbon would make here these 2 single bonds to these 2 cobalts, and this carbon here would make these 2 single bonds to these 2 cobalts. Okay, so you see how your electrons have been reutilized. Okay, now we can even do this for a third time, and then we get at this very interesting molecule. And this molecule can be conceived as a Cyclopropaneurian Complex, okay, in which we actually have a cyclic ligand that binds side on to a CO3 fragment. So in this case, we would have in this ligand formally a carbon-carbon double bond, okay, and an additional radical pi electron. So overall 3 pi electrons, okay, and these 3 pi electrons would now be used in order to make 3 carbon cobalt single bonds. Okay, this here is the first one, this one here is the second one, and this one here would be the third one. Okay, so formally you can conceive this complex as a complex between a cyclopropaneurian radical and a CO3 fragment. Okay, so last but not least, we can also substitute the 4th orbitalic fragment, and then we would arrive at the organic molecule tetrahedride. So I wanted to say that the picture of the side-on binding of alkenes or alkynes to the carbonyl fragment is not just a formal one. There's actual reality behind this, because one can even synthesize these carbonyl clusters this way. So for instance, if you wanted to make this tetrahedral cluster here that we have seen previously, that can be conceived formally as an alkyne binding side on to a dimeric cobalt carbonyl unit, then you can even make this molecule this way by starting out from an alkyne and react it with the cobalt carbonyl dimer, and then under loss of some CO, your cluster would form. Okay, so your cluster would lose 2 CO ligands, and your alkyne would bind with its pi electrons to the 2 cobalt atoms. All right, So finally, I wanted to talk briefly about another interesting class of carbonyl compounds. These are carbonyl hydrides. So a hydrogen ligand is a ligand which, according to the concept isotopicity, has one frontier orbit with one electron in it. So that is simply because, well, a hydrogen atom has the 1s orbital as a frontier orbital, and it has one electron in it. Okay, it tries to fulfill the duet rule. So therefore, it tries to make a single bond with another fragment in order to fulfill the duet rule. So therefore, a hydrogen ligand can be considered to be isolobal to a 17 valence electron organometallic fragment, okay, which is also one frontier orbit with one electron in it. So that means then it should be possible to combine a cobalt carbonyl tetracarbonyl fragment, which is a 17 valence electron fragment, with a hydrogen fragment to make what is called a carbonyl hydride, okay, HCO4. And indeed, this is possible. One can synthesize such a compound from the trimeric carbonyl and hydrogen at elevated temperature. So interestingly, this molecule, even though it's called a hydride, it is actually not hydridic properties. It's actually quite acidic, so it loses protons very easily. And the reason for that is that the respective anion that results is a pretty stable anion with 18 valence electrons. Okay, so HCO4 is a strong acid with an acidity similar to sulfuric acid. Okay, so now one can engineer the acidity of these carbonyl hydrides just by the proper choice of the metal and the choice of the other ligands. So for instance, we replace the cobalt by manganese, then the respective 17 valence electron fragment would be manganese CO5 fragment. So we would expect a stable hydride of the composition MnCO5H. And again, you could make it from the respective dimeric carbonyl and hydrogen at elevated temperature and pressure. So the energy levels of the manganese is of course not the same as the energy, exactly the same as the energy of the cobalt. So the highest occupied molecular orbit of the MnCO5 fragment has a different energy than that of the COCO4 fragment. Therefore, the polarity of the metal hydrogen bond is different, and as a result of that, also the acid-base properties of the molecule are different. So in this case, we still have an acid, but the strength of the acid is not as previously the strength of sulfuric acid, but only the strength of a weak acid such H2S. And like I said previously, one can now engineer the acid-base properties of these carbonyl hydrides from highly acidic, being a strong H+ donor, to highly hydridic, depending on the choice of the metal and the other ligands. Okay, these ligands can be carbonyl ligands, but you can also have other ligands. So for instance, a phosphine ligand and other ligands that influence the energy of the HOMO of the organometallic fragment, which then regulates the acidity of the respective carbonyl hydride. Okay, then let us move now a little bit away from the carbonyl ligand, and let us look at a number of ligands that have some relationship to the carbonyl ligand, and let's think about the similarities and differences in the chemistry of these ligands. So one pretty similar ligand is the cyanoligand, Cn-. So it's isoelectronic to the CO ligand. So the nitrogen has one electron less than the oxygen. So in order to be electronic to CO, the Cn fragment has to have one negative charge, and that makes it as a negatively charged cyanoligand. So now we can think about the properties of such a cyanoligand relative to the carbonyl ligand. So for instance, we can think about, well, which one would we expect to be the reactive end? Okay, so now I mentioned already previously that the MO diagram of the cyanoligand is very similar to that of this CO ligand. So as previously, we have the highest occupied molecular orbital, which is primarily located at the carbon. And for that reason, again, the carbon end is the more reactive end, despite the nitrogen having the higher electronegativity. So we can also think about, does the cyanoligand have stronger or weaker sigma donor properties than the CO ligand? Now, we can answer this question also relatively easily. The cyanoligand has a negative charge, okay, and as such, it has a greater tendency to donate electrons. Okay, so for that reason, the sigma donor properties of the cyanoligand is larger. Okay. We can also ask, well, do we have a stronger or weaker Pi acceptor? So by similar arguments, we can say, well, we would expect that this molecule is a weaker acceptor because it's already negatively charged. Okay, so it has less much tendency to Pi accept electrons. In addition to that, the electronegativity difference between the carbon and the nitrogen is smaller, and therefore the pi star orbital of the cyanoligand is less much located at the carbon. And for that reason, the overlap of the empty pi star orbital of the cyanoligand with the metal d orbital is actually less much. Okay, because the pi star orbital is more evenly distributed over the carbon and the nitrogen. All right, so last but not least, are cyanocomplexes more stable with metals in high or low oxidation states? We've learned that CO ligand really stabilizes metals in low oxidation states. They can even be highly negative. So would we expect that also with the cyanoligand? What do you think? Sorry?
Would it be more stable with the higher oxidation states?
Yeah, so in this case, the cyanoligand acts differently. It likely makes stable complexes with metals in positive oxidation states. Again, the most simple explanation is electrostatic. The cyanoligand is anionic. So, because there's Coulomb attraction between a cyanoligand and a metal in a positive oxidation state. An additional argument would be that the cyanoligand makes weaker Pi Acceptor interactions, which in the case of the carbonyls are very important to stabilize the metals in the oxidation state, because the ligand can accept electrons from the metal. That's less pronounced in the case of the cyanoligand. Okay, so let us go to another ligand, which is the nitrosyl ligand NO. So this ligand is not exactly isoelectronic to CO, because, well, the nitrogen has one more electron than the carbon, and for that reason, the NO has one more electron than the CO. Now that also makes the NO what is called an odd molecule or a radical. So if we wanted to write the Lewis dot structure, we would write in the neutral NO molecule a nitrogen-oxygen double bond. We would have 2 electron lone pairs at the oxygen. Then we would have 1 electron pair at the nitrogen, and then an additional radical electron at the nitrogen. The radical electron is necessary so that the nitrogen is surrounded by 5 valence electrons to make it electroneutral. So now, because of that radical nature, the coordination chemistry of the nitrosyl ligand is, well, of course, not exactly the chemistry of the carbonyl ligand. In fact, we can have 2 binding modes for the nitrosyl ligand. It can be either a 1 electron donor or it can be a 3 electron donor. When it's a 1 electron donor, it utilizes only the radical electron here at the nitrogen. And when it's a 3 electron donor, it utilizes all 3 electrons at the nitrogen. So now, what it does is largely guided again by the 18 electron rule. Okay, it utilizes just the number of electrons it needs to fulfill the 18 electron rule under normal circumstances. Okay, so now when it acts as a 1 electron donor, then the electron lone pair here at the nitrogen remains inactive in the bonding. And for that reason, the respective complexes have a bent structure, because the electron lone pair here is directly active. So an example for this is this complex here. So this is in chloroethylenediamine, nitrosyl, cobalt, cation. Then you see that there is an angle between the cobalt, the nitrogen, and the oxygen. And this metal nitrogen oxygen angle usually varies between 119 and 140 degrees. We observe in aspectotypical NO stretch vibration the range from 1520 to 1729 wave numbers. So when we have the nitrosyl ligand as a 3 electron donor, then, well, we bind the ligand in a linear fashion, because now we do not have an electron lone pair here anymore, which is directly active. All the electrons are involved in the bonding. So an example for this is this molecule here. So this is derived from the hexacyanoferrate, but one Cn minus ligand is substituted by an NO ligand, which utilizes 3 electrons. And you can see this from the fact that the metal nitrogen oxygen bond angle is nearly 180 degrees. Okay, so typically the bond angle can vary between 165 and 180 degrees, and the NO stretch vibration is between 1610 and 1680 wave numbers. Okay, so there's another view on that. So we could also explain this band structure a little bit in a different way. We could say, well, in this case, we assume that our ligand is not a neutral nitrosyl ligand, but an NO minus anion. And an NO minus anion would, of course, have an additional electron. So we would have then 2 electron lone pairs at the nitrogen, and that ligand would then use one of the 2 electron lone pairs to make the bond. So this is just a different formal perspective on the same issue. There's also different perspective to explain the linear complexes. So one could also formally argue that we have an NO plus ligand that acts as 2 electron donor. If we have an NO plus, then this radical here, radical electron doesn't exist. We have only this electron lone pair here, and the NO plus ligand would utilize this electron lone pair in order to bind linearly to a metal. Okay, so we could also ask, well, why can a neutral NO not be a 2 electron donor? Can you think of this? The answer?
Maybe if it was just 2 electrons, it would make that radical and would be very simple.
Yeah, so in other words, the radical electron is always the most reactive electron, so it's always utilized first. So it's actually electron in the highest occupied molecular orbital. And the more energetic electron is always being used first before any other electron can be used. Okay, now finally, let us have a look at phosphine ligands. So the phosphine ligands also have unique properties. At the first glance, you would think that they would behave similar to amine ligands, NH3, but in fact they do not, and that's because of a subtle difference in the molecular orbital diagram in phosphine versus ammonia. So you see the 2 molecular orbital diagrams here for ammonia and for phosphine over there, and you see that the bonding molecular orbitals are pretty much the same here. We have the 1A1, and then we have these 2 1E orbitals, and we have the 2A1 as the highest occupied molecular orbitals. Okay, so these correspond to the electron lone pairs in the valence bond picture. But you see there is a small but important difference with respect to the LUMO. So because the 3s and the 3p orbitals have different energies than the 2s and the 2p orbitals, the relative order of the 2e and the 3a1 orbitals are being swapped up. So for the NH3, the 3a1 is the LUMO, and for the pH3, the 2e is the LUMO. And now these 2e orbitals are energetically low enough so that they can interact with metal orbitals in particular, they can interact in Pi Acceptor interactions. So for that reason, phosphines can act as significant Pi acceptors, while the amine ligand does not have these properties. So I see our time is over, and we will elaborate a little bit on that further in the next class before we move on to organometallic reactions and catalysis. Okay, then let's stop at this point.